Good morning, and welcome once again to the Hawaii Transportation Energy Analysis webinars. My name is Anup Bandevadekar. I'm the Passenger Vehicle Program Director at the International Council on Clean Transportation. And today's webinar is about marine efficiency options that we are evaluating for the Hawaii Clean Energy Initiative. And I'll say a few words about that at the beginning before we get into today's topic on marine tactics. Just for those of you who have not been a part of these web events previously, let me just introduce the ICCT to you and tell a little bit about the project that we have been undertaking. The ICCT is a not-for-profit research institution whose goal is to provide unbiased information to policymakers and policy shapers around the world on reducing the environmental impact, both in terms of air pollution and on fuel consumption or climate change side of transportation. We work across the world on all modes of transportation, mainly on cars and trucks and buses, but also on aviation and marine sectors and the fuels that go with them. This particular project is something that has been sponsored by the Department of Business, Economic Development, Tourism, to help the State Energy Office with the analysis of the transportation efficiency options for the Hawaii Clean Energy Initiative. And so ICCT is presenting these views as our intermediate steps in the analysis in order to solicit feedback and input from all of the stakeholders. So just to set the stage about where this project is and what the background is, I'll go through this stuff quickly because most of you are likely to be aware of this material. But to recap, in 2011, the Hawaii Clean Energy Initiative established a roadmap with a pretty aggressive goal to reduce petroleum consumption from on-road sources. And the tactics underneath that goal were really fourfold in terms of reducing the amount of distance traveled, incorporating more renewable fuels, improving the efficiency of vehicles, and of course getting the electric drive vehicles into the fleet. And pretty ambitious near-term as well as mid-long-term targets were set for it. As we've looked back onto those targets, now we find that some improvement has occurred, definitely in terms of meeting the efficiency target, in terms of keeping the renewable fuel consumption at the same level. The sales of electric drive vehicles are not as high as anticipated in the initial roadmap. And there has definitely been a rapid increase in vehicle miles traveled as the economy has rebounded in this time. As a part of this particular project, we are considering a whole suite of policy options under different headings. And these really are efficiency improvements in light and heavy duty vehicles, electric drive vehicles, alternative fuels, including biofuels, natural gas, management of vehicle demand, and improving aviation and marine tactics. The last two in particular were not a part of the previous HCEI, and this particular time we are trying to incorporate several aviation and marine tactics. The way the project has moved forward is many of you might have attended the stakeholder workshop in Honolulu in November, and details of that are available on the website. We did first one of the webinars as a follow-up on vehicle efficiency tactics in about a month ago. Followed that with a workshop on electric drive vehicles held physically in Honolulu, January 13th and 14th. And then we had a web meeting on aviation tactics last week. So this is the final web meeting in this series on marine-related tactics. And in the coming months, we will continue with the evaluation of the tactics discussed here, taking into account all of the feedback that we have been receiving in these webinars and in physical meetings, and try to refine our analysis further. At some point of time in May timeframe, there might be another workshop physically in Hawaii to go and present the work that we are doing between now and then, before coming up with a final report in June timeframe. So that really is the background for the project. And I'm about to turn it over to my colleague Haifeng Wang to present today's analysis. Haifeng is a senior researcher at the ICCT and a core marine research staff here. Before I do that, just a couple of housekeeping announcements. All of you, as you know, are likely in the mute mode, and you will be in the mute mode until Haifeng's presentation is complete. If during this time you have any questions, please use the questions pane in your GoToWebinar control panel. So on the right-hand side, you should see a questions pane. You may also use the chat window. So feel free to use either of those, but the questions window, the questions will come to us and we'll answer those as they come out. And I'm hearing that there are some problems with sound, and we'll see if we can work through those going forward. So without further delay, I will hand it over to Haifeng, and please do let me know in the chat window or the questions if the sound problems persist. Haifeng is in a different location than I am. And so Haifeng, I'm now going to give you the keyboard and mouse control. And so you should be unmuted at this stage also. So please continue.
All right, thank you very much, Anup. And good morning or good afternoon, everyone, depending on where you are. This is Haifeng Wang. As Anup said, I'm a researcher at the ICCT shipping team, marine team. So I guess I will start off my presentation today with a broad overview of the baseline marine energy consumption. That constitutes two parts. And the first part is the bunker sales to ocean-going vessels. Let's see whether I can use the mouse here. Well, all right, great. And the first part is bunker sales to ocean-going vessels, which includes the fuels includes distillate and residual oils. And the second part is the fuel sales to smaller boats, which include ultra-low sulfur gasoline and ultra-low sulfur diesel. Okay. And for the bunker sales to ocean-going vessels, we can see on the graph that the fuel sales fluctuate widely in the past 3 decades, and it spiked near 2006, 2007, and then subdued around 2010 or 2011. In 2013, there's about 110 million gallons per year being sold to ships, ocean-going vessels. That is 2.5% of total U.S. bunker sales, and also accounts for 10% of total liquid fuel sales in Hawaii. Next slide is about the fuel cells to smaller boats. Oops. Okay. As we saw, there's equal volatility for the ultra-low sulfur diesel sold to smaller boats, but there was steady growth of gasoline sold to smaller boats. Around 2013, about 2.5 million gallons per year of diesel and gasoline being sold to smaller boats in Hawaii. Next slide, we talk about in the next slides, we try to combine these four types of fuels. But because there are four different types of fuels, we converted them to energy content in terms of British thermal unit. And you can see from the graph, the bunker sales to ocean-going vessels really dominate the total energy sales in Hawaii to ships. And we also applied a 5% annual growth between now and 2020 to come up with the baseline fuel sales to ships by 2020. That is 122 million gallons per year to ocean-going vessels, and 3 million gallons per year for smaller boats. Next slide. In the next section, we are trying to really look at how the ship operate and how the shipping energy consumption differ from other transportation sectors. The next slide, we in the past several slides, we already talked about four oils, and not all oil is the same. Especially for residual oils and distillates, they are at the bottom of the refinery process. Normally, they contain more sulfur, and they are much cheaper. Conversely, the ultra-low sulfur diesel and ultra-low sulfur gasoline are much cleaner, contain much less sulfur, but they are much more expensive. Next slide. And there's a sea change for the shipping industry as well in the coming years. Actually, in this year, starting from this year, ships that visit North America has to use much cleaner fuel. That is marine gas oil, which contains about 0.1% sulfur. Ships operate elsewhere has to use 0.5% marine diesel oil starting from 2020, although this regulation could be postponed to 2025. Between now and 2020 or 2025, ships operating outside of North America still use residual oils that has a sulfur content no higher than 3.5%. So in other words, we expect that in the coming decade, there will be more demand for distillate and less demand for residual oil. Next slide. We talk about alternatives all the time, alternative fuels, especially liquefied natural gas or LNG, as a potential alternative marine fuels. From a dollar per energy perspective, it makes much sense. The price of LNG is about half of the low sulfur fuel for ships. But from another perspective, the natural gas price in Hawaii is pretty high. Actually, the price to power plant is about 3 times of the national average. In other words, perhaps the power plants is more willing to pay for the natural gas than the shipping sector. And shipping does leave less LNG for the shipping sector to consume. Next slide. more importantly, I guess this is one key part of for the ocean-going vessels that differ from other transportation modes. That is, ocean-going vessels are able to carry sufficient amount of oil or fuel to visit multiple ports without bunkering. This is a very important point to remember, that because the energy reduced does not equal to the reduction of fuel cells. Although in this analysis, we assume actually the energy savings will translate to lower energy demand in shipping in Hawaii. More importantly, we need to bear in mind that the reduced fuel cells does not mean reduced transportation activity. This is a very important point that we are going to revisit in one of the tactics we are going to present. Next slide. So in the following section, we are going to evaluate several energy-saving techniques for ocean-going vessels and for smaller boats. And this study, this technique evaluation is actually based on the marginal Bateman cost curve that we developed a few years ago, which comprehensively look at the cost and benefit of 22 technologies and operational matters that could be applied to international shipping. Now let me pause here and see whether there are some questions that has been raised in the process.
So Haifang, only one clarification question came in about whether Navy fuel use is included, and my understanding is that it is not included in these numbers.
I'm sorry, which one is included?
Navy.
Navy, yeah.
Yeah, and these are not, so military fuel use is not considered in any of these measures.
Exactly. Yeah, it was not considered here.
Okay, at this time, we don't have any other clarification questions that have come in, so you could proceed.
Okay, cool. Next slide. So we actually, among these technologies and operational matters, we zoomed in and identified 5 strategies or techniques that we are going to consider here. Slew steaming, fuel surcharge, hull cleaning, propeller polishing, and onshore power. Next slide, we are going to talk about slew steaming more specifically. Actually, slew steaming has been used by several ports in California to reduce air emissions and energy consumption there. The idea is that main engine fuel consumption scales with the cube of operational speed. In other words, if you reduce the operational speed of your ship by 10% from the design speed, you may reduce the fuel consumption by 11% or more. Next slide. One difficult part here is actually we don't have the energy consumption for ships visiting Port of Honolulu. So we actually use the energy consumption from Port of Long Beach, as well as the relative cargo throughput from Port of Long Beach and Port of Honolulu. We assume a 5% increase of cargo growth between 2011 and 2020. That is in line with EPA's assumption when they applied for the emission control area to the International Maritime Organization. We also assume that ships will reduce speed to 12 knots when they enter the speed limit zone. We also assume that the Port Authority will encourage ships to reduce speed by reducing port dues to encourage ships to reduce speed voluntarily. So by this measure, we think that ships could reduce diesel consumption by 0.8 million gallons per year. And the Port Authority will hand out about 0.5 million US dollars in the form of discounted port dues. That translates to 61 cents per gallon cost. Next slide. Next, we're going to talk about fuel surcharge for shipping fuels suiting Hawaii. Next slide. As you can see that the tax for smaller boats and the marine bunkers are relatively low than other transportation fuels. Next slide. And it's even more important to note that the reduction of the bunker sales does not mean a reduction of transportation supply. Actually, if you can recall in slide 10, there was a spike of the bunker sales around 2006 to 2007. The reason was that the bunker price at that time in Hawaii was cheaper than elsewhere. So that attracts a lot of ships visiting Hawaii purely for bunkering purpose. And now, as you can see the graph below, that the price advantage has disappeared. But again, the transportation supply has not declined, just because ships make sure that they carry enough fuel in their tanks to finish the loop without bunkering in Hawaii. Next slide.
So Haifeng, just to clarify
Yep.
this point, uh, what you are saying is that a small increase in the price of fuel placed uh, at Hawaii will not necessarily affect the number of shipments or the tons of goods that enter in and out of Hawaii's ports, but will just affect how much demand for bunker fuel that takes place within Hawaii. Is that correct?
Yeah, that's great clarification. Yeah. So anyway, we talk about the fuel is a fuel surcharge to increase the fuel price. And based on other literature, we identified that about 1% increase of fuel price might reduce fuel sales by 0.15%. And we also assume that by 2020, the fuel price is $700 per ton as our baseline fuel price. So a $20 fuel surcharge equals to about 4% increase of the fuel price. And that translates to about 0.9 million gallons per year reduction in fuel sales in Hawaii. And because we bring in more revenues through the fuel surcharge, the cost is actually minus 10 cents per gallon. So perhaps the government could use the revenue for the fuel surcharge to support more energy-saving businesses, including the hull cleaning and the propeller polishing business that we're going to talk about in the next few slides. Actually, well, many ship owners, they clean their hulls and polish their propellers regularly. If you look at next slide, this practice could be used to reduce resistance in ship operation and thus reduce energy consumption for ships. But there's also evidence that shows many ship owners do not follow the regular schedule. So the difficult element is really to determine how many ship owners follow the schedule and how many ship owners do not. Next slide. And we have some information about energy reduction potential for hull cleaning and propeller polishing, as well as their cost. And we also assume that 60% of ship owners actually follow the schedule at the first cut. But we also did a sensitivity analysis, assuming that 60% to 90% of ship owners already use the hull cleaning or the propeller polishing practice. And we calculate the energy consumption, energy reduction potential for both ocean-going vessels and smaller boats. Next slide. And then we estimate that about 3 million 3 million gallons per year of diesel, marine diesel, could be reduced by 2020 from hull cleaning alone. And because using hull cleaning substantially reduce fuel consumption, we expect a negative cost, which is minus 47 cents per gallon. Similarly, we expect about 2.9 million gallons per year of marine diesels could be saved through propeller polishing, with a cost of minus 67 cents per gallon. And the graph below shows a sensitivity analysis in terms of fuel reduction potential based on different assumption of penetration rates from 60% to 90%. And the cost and energy reduction mentioned above is based on 60% penetration rate. Next slide. Last but not least, we also look at onshore power for ocean-going vessels visiting Port of Honolulu. Next slide. The onshore power is actually a technology that substitutes fuel oil consumption from auxiliary engines when ships are at berth for electricity onshore. Therefore, in order to quantify the energy reduction potential and the cost, we had to make a few assumptions about utilities in Hawaii. We assume that the capacity factor of utilities in Hawaii is 60%, and the renewables in the generation mix by 2020 is 25%, in line with the renewable mandate by the federal government. We also assume that 80% of ships will use onshore power by 2020 in Port of Honolulu. That is actually a figure mandated by California Air Resource Board for all the ships visiting ports in California. Again, we don't have the energy consumption for ships at berth in Port of Honolulu, but we use the number from Port of Long Beach calibrated through the cargo throughput. Based on these assumptions, we estimate that onshore power could reduce the marine diesels by 0.1 million gallons per year with pretty high cost. Next slide. And the reason for the high cost have several folds. First of all, over 2/3 of electricity was produced by oil by 2012, and over half of them is actually diesel. In other words, we are using much more expensive diesel to replace much less expensive residual oil. So that's not good business. And the only part to reduce the fossil fuel is through the 25% renewable mandate. And of course, this mandate could be raised in the future, which will further reduce fuel consumption by the onshore power techniques. But for now, we use 25%, and the reduction potential is not optimistic. And this situation was aggravated by the fact that the electricity price in Hawaii is relatively high. It's about 3 times as high as the national average as well. So that leads to even less favorable economic calculation for the onshore power. Next slide.
So Haifeng, onshore power is at some level required in ports like Long Beach for environmental reasons. That would be for air quality purposes.
Yeah. So onshore power is actually is more a matter to reduce air emissions at the ports. It's because when you shut down the auxiliary engine, you don't need to burn that very dirty fuels. So it's almost a zero emission technique. but from an energy reduction perspective, it's not that optimistic or that favorable.
Okay. We have a question from Ben Sullivan here about what is the assumed electricity price for this analysis. Whether there is a way to think of this as a dispatchable load for the utility, and so that would make a difference.
Yeah. This analysis used 30 cents per kilowatt hour as electricity price.
Okay, so when we get to questions, maybe I'll ask Ben if he has a follow-up to this.
Okay. So if we strip off the onshore power and only consider the steaming, propeller polishing, hull cleaning, and fuel surcharge, we estimated that about 5.1% of energy consumption could be reduced from the shipping sector by 2020, and that represents about 10.4 million gallons per year by 2020, considering the increase of the ship activities between 2020 and 2030 is about 14 million gallons per year energy reduction by 2030. Next slide is a table that summarizes the 5 tactics, their fuel savings estimate, and their cost effectiveness. In the next slide, that is, if you have more information, please feel free to visit the links, ask questions from the webinars, or shoot me an email or Dan emails for more questions after the webinar. Thank you.
There is a question from Stan Osserman about whether propeller polishing and hull cleaning require dry docking. If not, is there a water pollution problem if it is to be done in Hawaii?
Yeah, that's a very timely question, I think. So they could be down in the dry dock period, and it's actually favorably do so that you do not need to take the ship out of business, so that you do not incur more cost. And there are some concerns about the water quality issues, and I guess the Hawaii government has a task force for propeller polishing and hull cleaning in that very topic.
So this is the Hawaii Department of Transportation Task Force?
It's I think it's a tri-party task force. I think it's intergovernmental agencies task force.
On the propeller polishing and hull cleaning work. And so your answer is effectively that it can be done during dry docking.
Yeah, definitely.
Great, thanks. At this point, we can take audio questions from the participants. So if you can there is this way of raising your hand, if you will, in your attendee panel. And so if you have a question, please feel free to raise your hand, and I can unmute you so you may ask your questions or make a statement or a comment. You can also feel free to just continue to type in any questions you may have at this point. I do see a hand raised from Abbas Gudarzi, sorry. So I'm going to unmute you. If you have a question, please go ahead, Abbas.
This thing running, then we're going to have a major problem. What do we go from there? And that was my biggest concern of going with Exelon versus non-Exelon. Okay? Because
I think Abbas is talking about something else at this point. So I think Ben, if you have a mic, I'm going to unmute Ben Sullivan. I think Ben has got a follow-up about shore power and that the cost that Haifeng you had seemed pretty high. So Ben, if you can actually go on it further.
Sure. I'm just ignorant of how that price was determined, and it did look very high. Understanding that it would be higher, it seemed, very, very high, and I just wanted to try to help or get some help understanding that.
Yeah, this is a good question. So I was shocked at the first place when I arrived at number as well. So we, our analysis is only as good as assumptions. So we had a bunch of assumptions behind the number. First, we have the, of course, the electricity price is 30 cents per kilowatt hour. Another major cost is the infrastructure cost by building the necessary infrastructure to bring electricity to the terminal. The third part is retrofittation of ships, because you have to retrofit all the ships with onshore with shore power infrastructure. The fourth part of the cost is maintenance and operational and maintenance cost. It's typically a 10% of the terminal retrofittation cost. I think that's the main four parts of the cost. And then we assume that these costs will be spread in 3 years. And the onshore power infrastructure can last 15 years. We also made assumption that the discount rate is 4% in the 15 years. So we did a discounted cash flow to arrive the cost of reducing 1 gallon of fuel. And to just give some references, California did some analysis to do the cost benefit, the cost effectiveness of reducing emissions from onshore power. And not only California, but some consulting companies also did similar studies for ports in California. And to reduce 1 ton of particulate matter, for example, it's not fuel, but particulate matter, because in California, the main concern is air emissions, it's not energy consumption. At some port, reducing 1 ton of particulate matter through onshore power is $1 million. So it's a pretty expensive strategy.
Haifeng, I mean, are there any changes that could be made at the policy level that might shift the economics here? Is it something with respect to maybe being able to write off investments in the shore power related equipment or so on, or the current economics do seem that the kind of incentives might not be cost effective compared with what other options we have on the marine side?
Yeah, I guess one quick fix is that we attract all the ships that are already with shore power to visit Hawaii. There's quite a few ships that already have the onshore power infrastructure. Onshore, but on ship side infrastructure, because they want to comply with regulations in California, and there are some incentive programs in Europe as well. So if we actually can attract ships that already has ship side infrastructure, we can avoid that part of the cost. Secondly, I guess it's very interesting to look at the different assumptions and see how these assumptions will affect the final calculation. I mean, the cost, especially the terminal infrastructure cost, could be greatly influencing the final cost or final cost effectiveness of the onshore power tactic. Mm-hmm. So yeah, if there's some learning curve that could be applied, like if people are already skillful enough after building infrastructure in Long Beach, in LA, in San Diego, they probably can reduce their cost when they build similar infrastructure in Hawaii.
Okay. Ben, do you have a follow-up here? You're unmuted.
Yes, very briefly. The only thing I wanted to add is perhaps in your report, if you could just show a more aggressive analysis of the numbers to have, so we have a range, and that would include a longer payback time, an assumption about the percentage of ships that might already have the infrastructure, and then a lower power price, just so that we could have an understanding of how those impact the analysis. That's all.
So if we could show the sensitivity to some of the factors, I think that'll be good to.
Okay. Good idea.
We have a question from Greg Gouge, and this is about fuel surcharges. And the question is, would the fuel surcharge simply be passed on to the consumers? So what he's saying is, so the cost of imports would just increase rather than incentivize the ocean-going vessels to reduce the fuel use. That wouldn't that happen? Just
Yeah, that's definitely. There's multiple ways for fuel surcharge to appear on the final bills of the consumers. It really depends on the competition and the willingness to pay by the consumers. So I have to say that it's very likely that part of the fuel surcharge might pass along to the final consumers, and part of them will be absorbed by the sellers of the fuels.
Okay, we have a question from Bob King. So Bob, you are unmuted.
Yes, thank you. I was wondering if you looked at diesel engine technology as in upgrading engines, and also drive technology in the course of either direct drive or diesel electric drive, and what those would add to the fuel consumption picture.
Okay, so more efficient diesel engines. Yeah.
Sorry, go ahead.
Go ahead.
Haifeng, you're
okay.
Yeah.
So on the diesel engine side, so on the shipping side, I guess there are two parts. One is the ocean-going vessels, and the other part is the smaller boats. So we didn't specifically look at the technology, diesel technology that could be applied to smaller boats at this stage, because it's just 2% of the total fuel consumption from the shipping sector in Hawaii. And on the ocean-going vessel side, our marginal building cost curve indeed looked at the cost and the benefit of using more advanced diesel technology. And the only reason that we did not include this technique was that I'm not sure of the capacity in Hawaii to help ship owners to retrofit diesel engines. It's typically done by pretty big shipyards. And it seems to us that the capacity might be lacking in Hawaii to achieve this technique. And conversely, in comparison, we thought that propeller polishing and hull cleaning are two measures that whose capacity could more quickly be built. Well, actually, there are many shops, not many, but quite a few shops already in Hawaii that specialize in hull cleaning and propeller polishing. So that's why we decide to demonstrate the hull cleaning and propeller polishing, but leave the diesel part out.
But Haifeng, now, I mean, you didn't explain, of course, we didn't take the time here to explain the energy efficiency design index and other activities happening at the IMO level. So do you want to say something about that and what kind of average improvements in efficiency of ocean-going vessels one might expect over the next 10 or 15 years because of the IMO level changes?
Yeah, I will say a few words about EEDI with one caveat. So what Anoop just said is called Energy Efficient Design Index, which was passed in 2011 by the International Maritime Organization to mandate that new ships delivered after 2015 should have energy efficiency 10% higher than the average of the past decade. And by 2020, ships delivered after 2020 should be 20% higher, and ships delivered after 2025 should be 30% higher. So that's great news, I think, for energy efficiency of ships. But the caveat here is that this mandate is only applied to new ships. And as we know, that bigger ships has pretty long lifetime, typically 25 to 30 years. So in the near future, the majority of ships visiting Hawaii would be non-EEDI compliant ships. And these ships, the diesel technology could still be applied to the non-EEDI compliant ships, but only I guess the concern is that whether there is a capacity to retrofit the ships.
Okay, we have a question from Rachel James. Rachel, please go ahead.
Thank you. You had mentioned for the onshore power piece, encouraging ships that are already, I guess, modified in that way to now take port in Honolulu. But I wondered if there's any information as far as what those type of ships, what their cargo is.
Yes, so actually there are, well, of course, onshore power is best suited for ships that visit a port more frequently. That's really from a cost perspective. So cruise lines and container ships are the best fit because cruise lines travel for a fixed route, and shipping lines have, the follow schedule and they call port several times a year. And according to, for the California Air Resource Board, most of ships that are encouraged to use onshore power are tankers, are cruise lines, ro-ros, vehicle carriers, and container ships. I guess has nothing to do with technology, but just from a cost-benefit perspective, because they more frequently visit a port, a fixed port.
Okay. Thank you.
Welcome.
Sorry, there is another question from Kawakahi Amina, and the question really is that you mentioned that the military fuel consumption were not included and why that is. And I guess, I could answer that question in the sense that we are explicitly sort of dealing with issues that could be dealt with at the civilian side of things. And so while some of the technologies and options might be applicable on the military side, none of the analysis that we are conducting actually includes military uses of fuel, which is not to say that it's not important from the Hawaii's perspective, but it's not something that we could include in the scope of this particular work. I I do have an announcement to make that Linda reminds me to do. I mean, these webinars are kind of our preliminary presentations of our work on these different tactics. And so should you notice that a particular tactic is missing, or that an option we should have evaluated, or the comment from Ben today that sort of that we could do better sensitivity analysis around some of the assumptions, those are all very, very helpful comments. So if you have any further questions or comments or suggestions for analysis or feedback, uh, can you please send those before the end of this month? That would help us to take those into consideration as we write these things up early into next month and change any of the analysis further. Let's see if you have any further questions at this time. And Haifang, I mean, based on what you heard, was there any additional remarks you wanted to make? Otherwise, we can bring this to a close.
No, I think that's a very good discussion, and I really appreciate that audience take time to listen to this presentation and raise great questions. And I guess, Dan, I look forward to more communication with you by emails. As Anoop said, if you have any questions or think that we should include some tactics, please feel free to drop us emails or calls.
The slides from the presentation will be available on the State Energy Office page or the HCEI web page, perhaps by early next week. And so please check there on Monday. And just a comment here, there is no question, last minute comment from Mitch Ewan is whether we should really just be thinking about addressing inter-island shipping under marine consumption, and that because the ocean-going vessels are so much more difficult. I mean, Haifang, do you actually have data on how much of the fuel consumption is really on ocean-going vessels as opposed to just inter-island?
Well, the ocean-going vessels, I do have data, and I guess inter-islands, we are talking about either smaller boats or ferries. And very interestingly, I guess almost all the Hawaiians know the story of a super ferry and how the super ferry went to bankrupt. So I guess I don't see a lot of or a sizable fuel consumption from ferries among the islands in Hawaii. So I think the fuel sales to smaller boats more or less capture this already. But if people think there's some ferry services or other services that I didn't capture, let me know.
Okay. No, the question is really about inter-island cargo, because all of the big ships would come into Honolulu port, and from there the cargo goes to all the different islands. And if there are different, we need to put on a different hat to think about fuel consumption in that phase. And so that's kind of the follow-up here, I guess.
Yeah, definitely.
Okay, that's actually a useful thing to think about as you write up whether any of those things will make a difference if you were considering sort of drawing your boundary slightly differently. So I'll give sort of the closing comment. Really came in from Stan Osserman about Mitch's point is really good, that mostly inter-island barges, and so do this shipping between Honolulu and other smaller ports in other islands. And so would using smaller containers or ferries be more efficient to do that? So I don't know if you have any offhand comment about that, or you would just want to consider that as you're writing it up. But in case you wanted to say something about it here.
Yeah, well, I don't have the number for specifically for Hawaii, but for the U.S. average, the barge is among all the transportation modes. The barge is the most energy efficient one. I think is on par with rail. And in terms of the CO2 per kilometers or ton miles, it about 5 times or 10 times more efficient than trucks.
Yeah. And so because if those are what are being used right now, you would imagine that the opportunities for improving fuel consumption on those would be quite small. Is that what you're saying?
That's true. Absolutely.
Okay. Great. Great. Thank you very much, everybody, and please look out for the slides to be posted on the website early next week. Thank you.
Thank you very much.